All right, let's wrap up chapter 11 with the discussion of intramolecular forces. Now, you have heard or you studied in intro chemistry class that there are three intermolecular forces. There's dipole-dipole, London forces, or they call them the London dispersion forces, and hydrogen bonds. These are intermolecular forces. These are attractions between molecules, not to be confused with bonds between atoms, like ionic bonds between the ions or covalent bonds. Very different here. Now, these are just attractions between molecules. Definitely not as strong as a strong covalent bond. Okay, so you can break these. But out of the three, hydrogen bonds are the strongest of the intermolecular forces. So on the board, I wrote definitions for dipole-dipole and London force, and then I will write down a definition for hydrogen bonds. Okay, so what is a dipole-dipole? Dipole-dipole are attractive intermolecular forces resulting from the tendency of polar, notice I've underlined it, polar molecules aligning themselves positive N to negative N. Number one, dipole-dipole only occur between polar molecules, no non-polar molecules. So remember how to determine if a molecule is polar or not. Look at the molecule, see if it's symmetrical or not, do the Lewis structure, and you can tell if it's not symmetrical, if it's got lone pairs around the central atom, you got a polar molecule there. If it's nonpolar, it can't do dipole-dipole. A really simple molecule like hydrochloric acid or hydrogen chloride, HCl. You remember electronegativity, chlorine is a lot more electronegative than hydrogen. So this is a polar covalent bond. So the electrons are not shared equally. The electrons are more attracted to the chlorine than they are to the hydrogen. So it makes this end of the molecule slightly negative, this end of the molecule slightly positive. So the way the HCl molecules are attracted to each other, this H slightly positive H plus is attracted to the slightly negative Cl minus, Cl here. This is slightly negative, this is not an actual charge, guys. This is just a partial negative and a partial positive. This, by the way, is not a hydrogen bond. Remember, a hydrogen bond, as we're going to learn in a little bit, the hydrogen has to be bonded to a fluorine, oxygen, or nitrogen, not to a chlorine. Okay, so this is not hydrogen bonding. This is dipole-dipole. And any polar molecule can do dipole-dipole. Okay, so it's an electrostatic attraction between the partial positive and partial negative. Okay, what is a London force or a London dispersion force? This is very weak. This is the weakest of the three intermolecular forces. It results from an instantaneous, very temporary dipole. So there's an attraction between these molecules, but it's not because there's this permanent partial positive and partial negative. It just happens for an instant and then it goes away. So the London forces are super duper weak, but the only reason they become of any importance or they're really effective is if you got a really big molecule, big surface area, big molecular weight. The bigger the molecular weight and the more the surface area, the more the London forces. Okay, so size really matters with London forces. If you've got two molecules and one is like, let's say you've got an oil molecule and it's 20 carbons long, and you have another organic molecule that's just 2 carbons long. Well, that one that's 20 carbons long, bigger molecular weight, bigger surface area, way more London forces. So it's going to be really hard to separate the molecules from each other and turn them into, for example, the gas phase. But with a small, teeny tiny molecule, very little London forces, really easy to separate the molecules. All right, so there's not a lot of attractions. Which molecules can do London forces? Everybody. Everybody, all molecules, polar and non-polar, exhibit London forces. They all do. Okay, now we'll move on to the strongest of the three intermolecular forces, which are hydrogen bonds. And as a biochemist, and when I teach organic and biochemistry, I always make a big deal and about hydrogen bonds. So my students always joke around and say, well, when in doubt, say hydrogen bond, because that's probably the answer. And they account for so many things in biochemistry. The reason DNA is double-stranded is hydrogen bonds. The reason proteins fold the way they do, big reason, is hydrogen bonds. So super important in many areas in chemistry. And for you guys, you need to know that they are the strongest of the intermolecular forces. So just let's write down what a hydrogen bond is. Hydrogen bond. Again, it's an intermolecular force, so it's not as strong as a covalent bond, but it is the strongest of the three intermolecular forces. A hydrogen bond occurs when a hydrogen is covalently bonded to a highly electronegative atom like fluorine, oxygen, or nitrogen. If you look at the electronegativity table, fluorine has a value of 4.0, oxygen 3.5, nitrogen 3. So these are the most electronegative, all right? Hydrogen is covalently bonded to a highly electronegative atom like fluorine, oxygen, or nitrogen, and is attracted to the lone pair of another fluorine, oxygen, or nitrogen. So for example, if we have a molecule of water, see this hydrogen over here? It's covalently bonded to an oxygen. So it's going to be attracted to the lone pair of another oxygen. This right here, this dotted line, that's your hydrogen bond. Okay? How many hydrogen bonds can a water molecule actually form? Well, when you look at it, this one can form a hydrogen bond with another water molecule. And then you could have another water molecule over here, forming a hydrogen bond here, and then another one over here. So you can see for each water molecule, you could technically have 4 hydrogen bonds, all right? What if I had a molecule like this? Can it hydrogen bond? No. Why not? Because the hydrogens are not bonded to FON, okay? When we're writing out organic molecules, you're going to see this maybe on OWL, and you'll see this on your exam. You can see a molecule that sort of looks like this, CH3, CH2, OH. If the H is attached directly to the O and basically to the right of it, like this, then you know that when you expand out the molecule, this happens to be ethanol, by the way, this can potentially hydrogen bonds. None of these guys can. But what if you have something that looks like this, CH3O, CH3? How are you supposed to know if any of these H's are hooked up to the oxygen? Well, if you expand it out, you'll see that you got the 3. Remember, carbon has 4 bonds. Oxygen, 2 bonds with 2 lone pairs. So, this thing here, none of these hydrogens can hydrogen bond. Okay? Now, if you had a beaker filled with this molecule, this happens to be dimethyl ether. If you have a beaker filled with a whole bunch of dimethyl ethers, you don't have any hydrogens attached to oxygen, so nothing can hydrogen bond here. Can everybody see that? Okay? But this one over here, a beaker of ethanol, yeah, sure, we can have this potential for hydrogen bond, because you'll always have a hydrogen hooked up with an oxygen in a beaker full of ethanol. You'd have millions of those, so millions of hydrogens that can potentially hydrogen bond. So I just wanted to show you that when we write down these formulas, you should be able to expand them out so you can see actually what's going on, okay? The hydrogen is always going to be placed to the right of the oxygen, fluorine, nitrogen when we're doing condensed structures, so you'll know if it is a hydrogen that can potentially hydrogen bond. See over here, no hydrogen to the right of the oxygen. Okay, so why are intermolecular forces so important? Well, they can help us explain a lot of phenomenon in with liquids. We can explain the vapor pressure, why one liquid has a high vapor pressure, one liquid has a low vapor pressure. We can explain boiling point, because if something has a high vapor pressure, it's going to have a low boiling point. Well, what causes it to have such a high vapor pressure? What causes it to have such a low vapor pressure? What causes it to have a high boiling point or low boiling point? The other thing that intermolecular forces explain to us are surface tension, and I'll explain in the next video what that means and how it relates to intermolecular forces, and viscosity. Why is it that some liquids are viscous and other liquids are not? Okay, so we'll get into all of that. And before I do that, let me just end this part with this. Let's say I had a molecule of oxygen and a molecule of hydrogen peroxide and a molecule of bromomethane. Okay, so, and I ask you, what type of intermolecular forces would these molecules do? Okay, well, oxygen, pretty nonpolar, right? Very symmetrical, nonpolar. What can it do? The only thing nonpolar molecules can do is London forces. Okay, what about hydrogen peroxide? Hydrogen peroxide's got hydrogens bonded to the oxygens. When you expand this out, you're going to see hydrogens bonded to the oxygens. So great. So let's say we have this. I'm not going to do the Lewis structure. I don't want to confuse you guys. But basically, this one's going to do hydrogen bond. It's going to have dipole-dipole because it's polar. You got lone pairs on the oxygens. And it's going to do London force. So it does all three of them. Okay. This one over here, this won't confuse you. You'll get this. This is not methane. It's bromomethane. So basically, this is a polar molecule because you have the difference in electronegativity here. So this one will do dipole-dipole and London force. So in the next video, we're going to be able to look at molecules, decide what intermolecular forces they do, and then based on that, we'll be able to say, okay, which one of these is going to have the highest boiling point? Which one of these is going to have the lowest boiling point? Which one's going to have the highest surface tension or the highest viscosity? Okay, so we'll go ahead and do that in our next video.